Today I'd like to talk a little bit about the heat capacity of substances and a quantity called specific heat. So they're both related to each other, and so I want to define both of them. Heat capacity and specific heat are really the same thing, but they just kind of have different units depending on kind of the information that you're given and the information that you need, so you'd use them both in kind of different contexts. So let's kind of talk about what they are, and then we'll do some sample problems with solving various parts of them. So, heat capacity, as is kind of intuitive from just the name itself, is the capacity for something to absorb heat. It's the amount of heat that's required to raise the temperature of a substance by 1 degree Celsius, or 1 Kelvin, because we know that the Celsius and Kelvin scale are the same in terms of the magnitude of the units. They have the same, size to them. They just start at a different place. And the equation for heat capacity looks like this, where we're relating it to heat, which is Q. And then C here is our heat capacity. And then delta T is the change in temperature, so it's the final temperature minus the initial temperature, as is all delta anything, right? Final minus initial. So if we're analyzing our equation here and thinking about units and what types of quantities we would need in order to find this, we can see that if we rearranged and solved for C, that I would have heat divided by the change in temperature. Now we know that heat is going to be in joules because that's our SI unit for energy, and temperature is going to be in degrees of Celsius or Kelvin. Now, of course, Kelvin is the SI unit, but oftentimes with thermodynamics, we'll use degrees Celsius because it's just a more practical unit. When I have a thermometer, I tend to have thermometers that measure in degrees Celsius. It's less often that I see a thermometer that measures in Kelvin. So we tend to see these types of calculations and quantities reported in degrees Celsius for temperature, even though we know that that's not the SI unit. Given that, then our units on C are going to be joules per degree Celsius, right? So, or per Kelvin, or joules per Kelvin, right? So energy divided by that change in temperature. How much energy does it take to raise the temperature of a substance? And of course, different things have different heat capacities depending on what they are. Are they metals? Are they non-metals? The compounds, how many bonds do they have in them? What types of elements do they have in there? What types of other materials are in there? Are they insulating or conducting? All sorts of things impact heat capacity. Now, specific heat, which is abbreviated sometimes with a lowercase s, I like to abbreviate it as SH just for clarity. So specific heat as opposed to S for seconds, because it's often a lowercase s and an S is a unit of time. So I try to make it more specific to specific heat by calling it SH. Now that's the heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin. So this has a specific mass component to it. And realistically, if we look at the relationship between these two, then we can see that the heat capacity is equal to the specific heat times the mass, right? So that kind of piece is built in. So we can kind of talk about it either way. It's either the specific heat times the change in temperature times the mass, or we'd have the heat capacity times the change in temperature, and they say the same thing. I've had students in the past like this equation because it looks like cat, which I think is sort of adorable. It's a good way to remember it. And then if you can remember that the heat capacity is the specific heat times the mass, then that'll get you here. So specific heat is the heat or the energy. Again, we're in joules there. This is our specific heat. This is our mass. Now this is something that always infuriates students, because in the beginning, when we're first teaching about, standard units and SI units, we say, well, the standard unit that we all use to measure mass is the kilogram. But in specific heat, we use mass in grams, not kilograms, so it's the non-SI unit. We use the base, and then of course this is change in temperature, so we have the final minus initial, which is again going to be in degrees Celsius or Kelvin, either one, because it's a difference. So the difference in those two scales is going to result in the same change, right? The same delta T. So just make sure that you have all of your units in the same unit for your temperature, and that will be good to go. Okay, now the specific heat of a substance, again, is measuring if I have 1 gram. So let's take water, for example. Water is going to be in a couple of the worked examples that we do here in a second. If I have a gram of water, which is about a milliliter, right? Like a cubic centimeter. So cubic centimeter, or a mill, if you have a good kind of sense of volume, has a gram of, or a mass of 1 gram. And so the amount of energy it takes for that water to go raise its temperature from whatever it's at to 1 degree more than that is 4.184 joules per gram degree Celsius. So if we think about our units here, then our specific heat is going to have units of joules per gram degree Celsius. And again, we can kind of see that if we rearrange and solve for specific heat, we'll be dividing both sides by our mass and our temperature, and we'll end up with units that look like this. Now 4.184 should be a familiar number because that's the relationship between calories and joules, which is what we in the United States use for our unit of measurement. So that 4.184 in building things around water is really important. And the specific heat of water is quite high. 4.184 is a pretty large number. And we know that water absorbs more heat energy than other things. It takes more energy to raise the temperature by 1 degree Celsius than it does other things. And we'll kind of talk about why that is in later future videos. Okay, so let's solve some calculations with them as promised. So we can solve problems that look like this. How much heat is produced when 45 grams of water decreases in temperature, going from 87 to 33 degrees Celsius. And some useful information is the specific heat of water here. So we're going to use our equation, which is Q is equal to the specific heat times the mass times the change in temperature. And so I like to solve these by sort of listing out the variables that I have. I have a mass, which is my 45 grams. I have a change in temperature, which is going from, here's my final, T final minus T initial, which gives me an answer of negative 54.0 degrees Celsius. So my final temperature is smaller than my initial temperature. I decreased, so that's going to give me a negative value of my delta T, which is going to be important kind of moving forward. And then I have a specific heat of water, which is 4.184 joules per gram degrees Celsius. Okay, so it's asking how much heat. So I'm solving for Q. And if I plug everything into my equation here, I get Q is equal to my 4.184 joules per gram degree Celsius times my mass, which is in grams, times my change in temperature, which is negative. And if we do some unit analysis here, we're solving for heat, we're solving for Q, so we're looking for units of joules at the end, because that's the way we measure energy. So if we have a joule per gram degree Celsius times a gram times a degree Celsius, that'll give me joules, so that's good. When I'm analyzing for significant figures, it looks like I'm going to be rounding to 3. And when I plug that in, I end up with negative 1.02 times 10 to the 4th joules. Now, when I look at the sign of this, we know that energy can't be negative. I can't have a negative amount of energy. But again, the sign means that the energy is being released. It's going from the system out into the surroundings. And so that negative sign indicates kind of energy loss or heat loss. We'll call that by the system to the surroundings. By definition. So we can tell, and we actually knew that it was going to be lost because of this word right here, right? How much heat is produced when I'm decreasing the temperature. So I know that heat is coming out, so I would be expecting that to be negative. And the other way that you know that is if we just think about this from a physical standpoint, water, in order to decrease its temperature, heat has to leave, right? It's at a higher temperature. I need it to get colder So heat has to leave the system into the surroundings in order for that system to cool down. And so we would expect this to be negative. All right, let's do another. What is the specific heat of an unknown metal that has a mass of that and absorbs this amount of energy? And we're raising its temperature from 25.44 to 49.99. Now, specific heat could be something that's sort of lookupable. It's one of the characteristics of a substance. So this is a useful way to determine unknowns, for example. So I'm solving for specific heat. I'm going to be using my specific heat equation times the mass times the delta T. So we're looking for specific heat. That's my unknown. My mass is given here, 25.92. My Q, the amount of heat that I'm absorbing, is 1595 joules. And then my delta T, I'm raising the temperature, so I'm going to be, my final is larger than my initial. 25.44 degrees Celsius, which is 24.5. Okay. So when I'm looking at this thing, it says how much heat is absorbed. So it's coming from the surroundings into the system. So I know that my heat is positive. That's an important thing to keep straight in all of this. And then when I kind of plug and chug here, I need to rearrange my equation and solve for specific heat. So the specific heat is equal to Q over my mass times my delta T. And if I plug in those values from my kind of analysis over here, I ended up with, and it looks like 4 sig figs, 2.507 joules per gram degree Celsius. You will never get a negative specific heat. There's no such thing. So remember that energy is not negative, but the negative sign indicates loss. So we need to keep straight our signs when we're doing these types of problems, because that'll have an impact on how we kind of what other variables shake out. For example, I can never have a negative mass. I can't have a negative amount of energy that something can absorb to raise its temperature. That just doesn't make any sense. So we need to think about the conventions then. I can have a negative delta T. I can have a negative Q, so long as we know that the energy is produced or released, or it's an exothermic process. Okay, let's do one more. What is the final temperature this time of this amount of water? So it starts at 22 degrees Celsius. It absorbs a certain amount of energy, and we're given the specific heat here, and it wants to know what temperature will it end up at. So I'm solving for T final. I have T initial, 22 degrees Celsius. I have the specific heat of water, 4 joules per gram degree Celsius. I have the amount of energy that is absorbed, so it's positive, 2,227 joules. And then I have my mass, 101.5 grams. Okay, so if we have our equation, Q is equal to our specific heat times the mass times the delta T. Hopefully you're kind of getting down the pattern here of what we're doing. Then we can unpack our delta T, and it'll look like this: specific heat times my mass times T final minus T initial. And I need to unpack it because I have 1 out of 2 of those variables. So now, depending on your comfort with algebra, of course, you can just kind of plug in the numbers and then sort of rearrange and solve. I like to kind of rearrange and solve for the variable. So if I'm rearranging this, I get T final is equal to the heat over the specific heat times the mass plus T initial. So if I'm plugging in the values that I have here, then I end up with 27.2 degrees Celsius. And I'm limited to 3 significant figures because of my temperature and all that good stuff. So we're absorbing energy. We would expect the temperature to be going up, and that's how we would solve problems kind of where we have one of those in the delta T part missing. So this is a good way to kind of look at how we can use these types of calculations, and it gives you a better idea of what specific heat is all about. And as always, if you have any questions, don't hesitate to reach out, and I'll talk to you again soon.